All right, ready to dive into some quantum mechanics?
Let's do it.
Today we're taking a deep dive into some seriously mind-bending concepts, and trust me, this is not your high school physics class.
Yeah, this is the stuff that keeps physicists up at night.
We're going to be exploring a simplified thought experiment based on the double-slit experiment.
Ah, yes, the double slit, a classic.
The one that really had, physicists scratching their heads for, like, decades.
A good reason. It really gets at the heart of the weirdness of the quantum world.
And what I think is so fascinating about the paper you shared is how the author like really captures that sense of wonder and disbelief, that the original physicists must have felt.
Yeah, it's like you read their work and you can practically feel them grappling with these ideas that just seem to defy common sense.
Totally. They even describe the atom as the, quote, protagonist in this mind-bending story.
Uh-huh. I like that. Because the atom in this experiment, it really does act in ways that are totally unexpected, almost like a character in a sci-fi novel.
Exactly. So to set the stage, imagine we have this machine and it randomly places a single atom into one of two boxes.
Okay, I'm picturing it.
And we've also got a detector, a device that can tell us if an atom is present in a box.
Pretty straightforward so far.
Yeah.
This is all still in the realm of classical physics, right? The physics of our everyday world.
Right, exactly. So in this first experiment, we run the machine, the atom gets placed in a box, and then we use the detector to check.
Man,
And as expected, we find the atom in one box and the other box is empty. No surprises there.
just like putting a coin in one hand. It can't be in both.
Okay, now let's make things a bit more interesting.
Okay, I'm intrigued. What's next?
For the second experiment, we're going to add a screen in front of the boxes.
A screen.
So when a box is open, the atom can shoot out and hit the screen.
I see. Like a target.
Yeah, exactly. We're basically seeing where the atom lands after it exits the box.
Got it. So what happens in this experiment?
We run it, and the atom comes out of the box where it was put and hits the screen, leaving a mark. And after many trials, running the experiment over and over, we get a pattern of marks on the screen.
So the atom's behaving like a tiny projectile, traveling in a straight line from the box to the screen.
Right, like if you imagine throwing darts at a board, most of them cluster around the bullseye, but some are more spread out.
Makes sense.
Yeah.
So far, the atom is behaving exactly as we'd expect.
But are you ready for the quantum twist?
Always ready for a good twist. Lay it on me.
Okay, so for the third experiment, we put the atom in one of the boxes. But this time, we open both boxes at the same time.
Ooh, okay. Now things are getting interesting. What happens now?
Well, if we're going with our normal everyday thinking, you'd think, like, either the atom comes out of the box it was in and hits the screen, like before.
Right, or we see kind of like a combined pattern
Yeah.
on the screen. Like if we'd run the second experiment twice.
Right, once for each box.
Yeah, once for each box. And just kind of like overlaid the results. Exactly.
Uh-huh. Here's where quantum mechanics throws us a curveball.
It does indeed. Instead of those sort of straightforward outcomes, we get something totally different. What emerges on the screen isn't a simple combo. It's like a whole new pattern.
A new pattern.
Yeah, an interference pattern with these alternating bands of like high and low concentrations of marks. It's almost like, waves interacting with each other.
Hey, hold on, waves, but we're talking about an atom,
Right.
a single particle, right? How can it act like a wave?
That's the million-dollar question. And it's the one that really shook the foundations of physics in the early 20th century. It's as if the atom, even though it's one thing, is somehow going through both boxes at the same time, creating this interference pattern.
That's so bizarre. Like, it just goes against everything we think we know about the world. It's like saying you can walk down two different hallways at the same time.
Exactly. And this is where the idea of superposition comes in. Quantum mechanics suggests that the atom isn't actually split in half, but it exists in this state of superposition.
Superposition.
Where it's potentially in both boxes, simultaneously.
Yeah.
Not that it's like physically divided, but that its existence is kind of spread out.
Oh, I see.
Like a wave across both possibilities.
So it's not like it's like zipping back and forth between the boxes really fast.
No.
It's more like it's in this fuzzy, undefined state of being in both places at once.
Yeah, that's a good way to think about it.
Oh.
And the pattern on the screen, the way it changes depending on how far apart the boxes are, it's like a fingerprint of this superposition state. It's the atom's way of saying, hey, I'm not limited to just one box here.
This is already blowing my mind, but the source mentions that it gets even weirder.
Yeah.
What's this about the observer effect?
Ah, yes. This is where things get really head-spinning. The observer effect basically says that the act of observing or measuring a quantum system can actually change how it behaves.
So they wanted to, like, catch the atom in the act,
Yeah.
see if it really was in both boxes at the same time.
Exactly. They added detectors to each box to try and figure out, like, which box the atom was coming from when both were open.
Uh-huh.
They wanted to see if this superposition thing was for real or just some kind of illusion.
Okay, and what did they find?
Okay, so are you ready for this? This is where it gets really crazy. The minute they added the detectors and tried to watch the atom's path, the interference pattern just disappeared.
It just vanished.
Gone. Poof. It was as if the atom was like, okay, fine. If you're going to watch me that closely, I'll pick a dox.
So just by trying to observe the atom, they changed the outcome of the experiment? That's almost like spooky, isn't it?
It is. It's like the act of measuring, of trying to figure out which way the atom went, kind of forced it to choose a box.
Yeah.
It collapsed that fuzzy superposition state into a definite result.
It's like the atom was playing hide and seek,
Uh,
and the second we turned the lights on, it had to pick a hiding spot.
yeah. That's a great way to put it. It really shows how counterintuitive quantum mechanics is. Because in our normal world, objects have definite positions.
Hmm.
They don't just kind of jump between possibilities depending on if we're looking or not.
So are we saying that, like, reality is undefined until we observe it?
Hmm.
Does our observation actually shape the world at, like, this really fundamental level?
These are like some of the biggest and most debated questions in all of quantum mechanics. And to be honest, we don't have all the answers yet. What we do know is this experiment shows a deep connection between the observer and the observed, between, consciousness and the physical world.
Right.
That's unlike anything we see in classical physics.
It's both fascinating and kind of unsettling at the same time, right?
Oh, yeah, for sure.
Makes you question everything you thought you knew about how the world works. It really does make you think, like, is there some kind of, like, fundamental limit to what we can know about the universe?
Yeah.
If just by looking at something we change it, are we, like, forever chasing a moving target?
It's a humbling thought, right? It suggests that maybe the universe is just, like, inherently uncertain at its core, that it's more about probabilities than, fixed certainties, and that our role as observers is way more intertwined with reality than we ever thought.
So it's not that the atom's being, like, shy or playing tricks on us.
No, no, no.
It's more that our attempt to, like, even look at it changes the rules of the game.
Exactly. It's kind of like, yeah, imagine you're trying to study a butterfly, but the only way you can do it is by pinning it down,
Oh, yeah.
The act of pitting it lets you see it in detail, but you've fundamentally changed it in the process.
That's a perfect analogy. It helps to understand why this whole observer effect is so hard to, like, wrap our heads around.
Mm.
We're so used to thinking of ourselves as, like, these detached observers separate from the world.
Right.
But quantum mechanics says that the line between the observer and the observed is way blurrier than we thought.
And that brings up all sorts of interesting philosophical questions.
Yeah,
It's
what
does this mean that consciousness, the act of observation itself,
Uh-huh.
plays some fundamental role in actually shaping reality?
Right.
Or are there other ways to, like, interpret quantum mechanics so they can explain these weird results
Yeah.
without having to bring consciousness into it?
I mean, that's what's so cool about this whole topic, right?
Oh, absolutely.
It's not just some abstract physics problem. It's like making us rethink our place in the universe and the very nature of reality itself.
It really is. It's a reminder that the universe is full of mysteries.
Right.
And the more we learn, the more we realize how much we don't know.
Okay, so we've gone deep down the quantum rabbit hole here.
Uh-huh. We have.
And it's clear that it's a strange and wondrous place where atoms can be in multiple places at once and where observation, like, literally affects the outcome.
It really is mind-boggling.
But what does this all mean for us, in our everyday lives? How does this quantum weirdness connect to the world we experience?
Yeah, that's the big question, isn't it? You might think that quantum mechanics is so far out there that it has no real impact on our lives.
Right.
But actually, quantum mechanics is the foundation for a lot of the technology we use every day.
Oh, really? I wouldn't have thought of that. Like, what?
Well, think about lasers, transistors,
Mm-hmm.
the chips that power our smartphones and computers.
Uh-huh.
All of those rely on the principles of quantum mechanics. Even medical imaging techniques like MRI wouldn't be possible without understanding how particles act at the quantum level.
So even though we're not, like, directly seeing quantum stuff happening in our lives, it's still working behind the scenes, like
Mm.
this hidden layer of reality that's powering our modern world.
Exactly. And as we keep exploring quantum mechanics, who knows what other amazing technologies we might discover. Quantum computing, for example, has the potential to revolutionize things like medicine, materials science, even artificial intelligence.
Oh, wow. So quantum mechanics is not only changing how we understand the universe, it's also driving technological innovation in ways that we're like just beginning to understand. That's incredible.
It really is. It just goes to show the power of human curiosity and our desire to understand the world.
Yeah.
And even though we might never fully grasp all the details of quantum mechanics, the journey of exploring it is just as amazing.
Well, that is a perfect note to end on. So, as we wrap up this deep dive into the quantum realm, what's one final thought you want to leave our listeners with?
How about this? Next time you're looking up at the stars, you know, marveling at the vastness of it all,
Yeah.
remember that even the tiniest particles, the atoms that make up everything we see and touch, they hold within them a universe of mystery and wonder.
A universe that challenges our assumptions, expands our imagination, and reminds us to embrace the unknown.
Exactly.
It's a beautiful thought that the journey of scientific discovery never really ends. There's always more to explore, more to learn, and more to be amazed by. And that, I think, is truly mind-blowing.